this talk will be about the interface between physics and mathematics, I would say. And these topics, though, are very much inspired by fundamental questions which can arise also at the level of neuroscience and brain research. And I'm here to discuss with you this recent recent findings. But of course, I hope it will be up to you to probably expand and find if really these approaches can have a real application into neuroscience. So there's been a lot of research and interest in networks. So we have heard in the talk before that networks are a set of nodes and links connected together. And of course, networks like brain networks represent a physical system, which is described by these graphs. And but recently there is increasing interest in higher order networks. So higher order networks are not just formed by node and links only, but also by many body interactions. So for instance, a triangle formed by the interaction between 3 nodes, or a tetrahedra, the interaction between 4 nodes. And these higher order networks come in different, they can be treated by different mathematical objects. Some are hypergraph and some are simplicial complex. And I will introduce a little bit of both, but I will then focus mainly on simplicial complex, and I will explain you why. So these higher order networks are attracting a lot of interest from the neurosciences perspective, and in general from the complex system perspective. And in this first paper, I hope you can see my mouse. So in this paper by Chad Giusti, Robert Gries, and Daniel Basset, is a very beautiful paper I will cite later on. They make the point that higher order interaction, if you look at brain region, can distinguish between 2 different situations. So when you have 3 brain regions that are correlated pairwise, or when you have 3 brain regions that are co-activated at the same time. So this is a difference between 3 two-body interaction and a 3-body interaction. And the whole talk is about taking into account this difference and describing this many-body interaction. I will take a quite abstract approach, but of course you can refer to this paper and to many other papers that are coming out at very high rate. So these are not only brain research, this is becoming very important, but also, for instance, in the biological realm, you have protein complexes. So, proteins do not perform a function alone. They need to have these protein complexes that are aggregated, aggregation of different protein, usually protein, more than 2 different protein, and only this complex is able to perform the function, right? So you can consider this complex as a many-body interaction. And also, well, in face-to-face interaction, you can have a group of people, and in collaboration, both in actor collaboration and scientific collaboration network, you might have more than 2 people, for instance, writing a paper together. So higher order networks really capture this higher order interaction. And they belong to a set of models which generalize network structures. So another very popular structure in which I work quite extensively is the multi-layer network. So you can have also in the brain, these are very relevant. So you can have, for instance, two regions of the brain connected via structural or functional connectivity, or two neurons connected via chemical or synaptic or gap junction connection, so electrical or chemical connection. And this is a all different chapter. I have wrote a book on the topics. I would love to tell you about these two, but for the moment here, I will focus on higher order networks, in which I'm working on it quite more recently. So higher order networks, you should distinguish between hypergraph and simplicial complex. So hypergraph are formed by hyperedge. The hyperedge is a generalization of an edge. So an edge is a set of two nodes. An hyperedge of size m is a set of m nodes. And so you have a 3 hyperedge or a 4 hyperedge between 4 nodes, and it indicates the interaction between these m nodes. So for instance, 3 people writing a paper together, or 4 people writing a paper together, to have a very concrete, simple example. So an hypergraph is a set of node and a set of hyperedge, and this hyperedge can be chosen arbitrarily. So you are quite free to choose the hyperedge depending on the data set you have in hand. So for instance, if you have a triangle 1, 2, 3, you might have a link 1, 2, but you might not have a link 2, 3 or a link 1, 3. Okay, so this is you can choose the hyperedge with complete freedom. Okay, so this is the main difference from, so for instance, you have 3 people that have collaborated on a paper, 1, 2, 3, they have co-authored a paper, but only 1 and 2 have a 2-author paper. The third person has not co-authored a two-author paper with any of the other one. So this is the difference with simplicial complexes. And simplicial complexes are formed by simplices. So a simplex of dimension d is a set of d+1 nodes. So for instance, a 0 simplex is a node, a 1 simplex is a link, a 2 simplex is a triangle, a 3 simplex is a tetrahedra, where these describe actually the interaction between these nodes. But most importantly, as you notice, I use this term, geometrical term, triangle, tetrahedra, because this simplices admits a topological and also a geometrical interpretation. So you can assign a length to the link, and consider these as triangle, tetrahedra, and so on. So, and they simplicial complexes, so the simplices have faces. So the faces of a simplex is a subset, is a simplex formed by a subset of its node. So for instance, if you have a tetrahedra, a 3 simplex, a subset of its node is a subset, is a face is either 4 nodes, 6 links, and 4 triangle. These are all faces of the simplicial complex. Of the simplex, sorry. And the simplicial complex is a set of simplices, little bit like the hypergraph is a set of hyperedge. But the additional condition is that it is closed under the inclusion of the face of every simplex. So if we look again at this triangle 1, 2, 3, the simplicial complex will contain this triangle, but also will contain, by definition, all the faces. So the links 1, 2, 2, 2, 3, and 3, 1, and the node 1, 2, and 3. And of course, you might say, well, this is a bit of a constraint because I'm not I don't know if all these interactions are there, but in general, this comes with a very good advantage of simplicial complex is that you can use a lot of tools coming from maths to analyze them. So as long as you understand, right, what is the object you are using, when you are using a simplicial complex, essentially you are stating that what are called the facets, so the simplices that are not faces of any other simplex, the higher dimensional building block of the simplicial complex, they describe a physical interaction. And then all the other faces might or might not describe a real interaction between these objects, but you would give more importance to the facet, so to the largest, the simplices that are not faces of other simplices. And here in this talk, we will focus mostly on simplicial complex, although we will mention sometimes hypergraph, because of course they have this advantage that they are really very rich structure to analyze and to perform some analytical and methodological study of the network. So an important question is, you know, what happens if I don't have this many body interaction, I have only a network and I want to use topology to study them? Or in another question you can have is, I have the many body interaction, but I want to use a lot of tools that I know already for a network. Can I go from a simplicial complex to a network? And the answer is yes. So there is a very clear procedure, and it's called the simplicial complex skeleton. This simplicial complex skeleton is the network form starting from the simplicial complex and retaining only the information about the node and the links. So you can go in one direction. Can you go also in the other direction? So from a network to a simplicial complex? And the answer is yes, you can go in the other direction. And the most straightforward way to do that is to consider all fully connected subgraphs, so triangle, you know, 3 nodes connected to each other, 4 nodes connected all to each other, 5 nodes connected all to each other, which are called cliques. And then you interpret each clique as a simplex. And in this way, you reduce your study of your network to a study of a simplicial complex, which is called the clique complex of the network. There is a little, you know, you need to be a little bit cautious with this operation, because if you concatenate this operation, you are not guaranteed to obtain the original result. So if you start from a simplicial complex, you do the network skeleton, and then you do the clique complex. As you see in this example, you know, in the original simplicial complex, there are some triple of nodes that are connected, but they are not connected in a filled triangle. While when you do this operation, they become connected in a filled triangle, and also you have a tetrahedra there, which is not originally present in the simplicial complex. So in general, when you do this operation, you can get more simplices than what you had originally. And this is important, for instance, if you start for instance, if you just start from networks which are scale-free, you know, that have a broad degree distribution, we had in the early day of network science some result that actually the scale-free degree distribution implies that the clique number, so the dimension of the largest clique, the size of the largest cliques diverges with the network size, also if the network is sparse. So when you do a simplicial complex, you will get a simplicial complex with very high dimension. Also, if you start with a network, right? And this remains valid also if you start from a simplicial complex, which is quite heterogeneous. You might have a lot of, not filled simplices there. So this is an initial introduction to the topics, and there are many review articles. The classic review article by Kale on models of simplicial complexes is a mathematical paper. Then this paper by Chad Giusti, Robert Gries, and Daniel Bassett, which merge between mathematics and neuroscience. Two recent review articles, and I think by fall I will have a Cambridge University Press book on the topic. So in this talk, I want to address one question, which is, I think, very crucial for the theory of networks, but also very crucial for neuroscience. And it is the interaction between structure and dynamics. So how the structural aspect of a network affect the dynamics taking place on it. And this has been a central theme in network science, but a lot of research, although there has been important work indicating that also the spectrum is important, but the most important result, the most prolific field, has been the one in which one observed that the statistical and the combinatorial property of the network affect the phase diagram of dynamics. So for instance, you have that, if you have a very broad degree distribution, like the scale-free degree distribution, it is robust to damage. So the percolation dynamics is important effect, is strongly affected. You have zero epidemic thresholds and all this. And I think I can point to you the very beautiful review by Dorodotsev, Goltsev, and Mendes on the topic. But when you look at simplicial complexes, actually, it seems clear that this combinatorial and statistical property are not only the only structural signature of the network that affects dynamics, and also a lot of richness comes for considering network geometry and network topology. And it's really the fact that higher order network are allowed to have this geometrical and topological description, which allows also to have a new perspective on dynamics. So I will cover the structure here in this talk. Let's see what I managed to cover. Stop me if you have any question. And the dynamics part will be instead covered in tomorrow's lecture. Do you have any question for the moment?
Any questions? No, thank you.
Okay. So let me just continue. So the first part will be the first part of this diagram. So a description of the structure of higher order network in terms of their combinatorial property and their geometrical and topological property. So a simplicial complex is associated with a dimension, which is the dimension of its higher dimensional simplices. So for instance, here, the facets are all triangle. So the triangle have dimension 2, so the simplicial complex will have dimension 2. Okay. And a simplicial complex is pure if it's only formed by d-dimensional simplices and their phase, like in this left example, and is not pure if instead there are d-dimensional simplices, but also simplices of dimensions smaller than d, which are not phases of simplices of dimension d. So for instance, this link 1, 5 is not a face of a triangle, so this simplicial complex is not pure. So in order to characterize the combinatorial and statistical property, of course, one idea is to have a generalized degree, a notion that generalizes the notion of degree. Degree is the sum of the link of each node. So the generalized degree, the delta of a delta phase alpha, is the number of d-dimensional simplices incident to that phase. So let's see in concrete. So K20 alpha is the number of triangle, so two-dimensional simplices incident to a node, zero-dimensional simplex alpha. K21 alpha is the number of triangle, two-dimensional simplices incident to a link alpha. Okay, so for instance, here you have this picture and you look at the generalized degree of the node, and for instance 3 is incidence to 4 triangle, so the generalized degree of 3 is 4. And then you look, for instance, at the link 1, 3, and the generalized degree of this link is 3 because there are 3 triangle incident to it. And this is listed to the table, just simply like that. So if you have a pure simplicial complex, you can describe the simplicial complex with a tensor, right? So instead of having an incidence matrix, which will tell you if a link is there or not, you have a tensor, for instance, here, three-dimensional tensor that will tell you if Rs and P is a simplex or a facet of your simplicial complex. So if the triangle Rs and P is present in the simplicial complex. So in terms of this tensor, the generalized degree is just the sum of all these 0 or 1 perform over all the simplex incident to the phase alpha. Okay, so I think here is A alpha prime. So you sum over all the simplices to look at the generalized degree of alpha. So sorry, there is alpha prime here. Okay, and this, they have a very nicely combinatorial property because practically if you know the generalized degree of some phases, d-dimensional phases, you can extract m-dimensional phases, you can extract the generalized degree of phases that have another dimension. And so one thing you might want to do is to have a model. You know, we will discuss a little bit about somewhat about model in this lesson. So one very important modeling framework is the one that leads to configuration model or exponential random graph in networks, for instance. And here I relate a bit to the lesson of the previous lesson, which introduced a random graph. So random graph are graph in which you fix in average the average number of links of a network because you fix the speed, the probability that two nodes are connected to each other. You have also another random graph in which you fix you know, the hard constraint that you consider all the network with exactly L links. And you can really go and expand this theory, finding similarity with physics and generalizing also to structure that are not graph, but for instance here in this case, simplicial complex. So I have a series of lectures devoted to this quite in detail in YouTube. But here I will just show you the application to simplicial complex. So what you have is for each simplicial complex, you assign a probability of the simplicial complex. So you consider all the set of simplicial complex that you can construct with n nodes, and then you assign to each of these a probability. And of course, when you have a probability, in order to assess the typical number of a simplicial complex in this ensemble, you can use the entropy, the Shannon entropy. And where you, instead of, you know, you have a probability for each simplicial complex, so you use the Shannon entropy for each simplicial complex. And then if you want to know the least unbiased ensemble in which you fix a given set of constraints, for instance, you fix the generalized degree of each node, either in average as a soft constraint or sharply as a hard constraint, then what you need to do is you maximize the entropy given the constraint. So you introduce some Lagrangian multiplier and you maximize the entropy. And what you get is that for the hard constraint, actually, the least unbiased ensemble is the ensemble in which you consider all the simplicial complexes which satisfy the constraint with uniform probability. And if the simplicial complexes which do not satisfy the constraint have zero probability of occurring. So this is what is called the microcanonical ensemble. Instead, if you fix the constraint in average, so you say in average I expect my node to have this generalized degree, then you get what is called in statistical mechanics the Gibbs measure, so this exponential random simplicial complex in this case. So the probability of a simplicial complex is 1 over a constant, a normalization constant, e to the minus lambda I. These are the Lagrangian multiplier enforcing the constraint, and then the constraint that you enforce in average. So there is all a procedure to treat this ensemble, and you can get the probability that the simplex is there, which is the corresponding of the probability that the link is there in a random graph. And you notice that this probability is not factorizable into contribution coming from each node of the network. So if you would have at the denominator only 1, this would be factorizable. But the fact that the denominator, you have this plus and this other exponential, it means that it's not factorizable. And this is a sign that these networks have some sort of so-called correlations. So, but if the degree, this generalized degree, are not too large, so if the generalized degree of the node has a bound, which is called structural cutoff, then you can approximate the denominator with 1, and then you get that the probability of a simplex is given by a normalization and then the product of the generalized degrees of the node belonging to that simplex. So this is a very simple expression which can be very beneficial, for instance, to do dynamical process on networks in this regime. But this is only an approximation. So yes, so this is a slide which practically summarizes the concept. You have this marginal probability, and then if there is the structural cutoff, it factorizes, and this structural cutoff is given by this expression. And you can look at this general theory, and you can reduce to the case of networks, and you have this quite famous now marginal distribution for exponential random graph. And here the uncorrelated expression, which is also quite famous. But with this general theory, of course, you can have also the case for d equal to 3, 2 and 3 and generalize in this way. So of course, what we want to do is we have practically node, right? And we say every node has a given generalized degree. So a given number, for instance, of triangle. So you put this tab on the node, and then you merge the node and according to the stub, in order that each triangle is incident to 3 nodes, so 3 stubs. So you merge the stubs, forming triangle. And then after you have done this kind of matching, you can construct the simplicial complex, because practically here you know that 2, 3, and 4 form a triangle. So you can find the simplicial complex between 2, 4, and 3, and so on. And of course, the whole idea of having an entropy of the network ensemble is the fact that actually from a given distribution of the generalized degree of the node, by performing this operation, you can get different simplicial complexes. So you want to a model which describes also the way to do this mapping, so the algorithm to do this mapping, and gives you the entropy, so the number of typical graph that you get in this way. And so so this is to iterate. So you have the node with the stub, you introduce some fictitious node that are the triangles with 3 stubs, and then you do the matching between those, and you form the simplicial complex. So you start matching 1, and then you go, you match, you know, all the stub of the first triangle, then you go and consider the second triangle. And this seems to work nicely, but you need to be careful, because the simplicial complex constructor is not totally equivalent to this. So in particular, there are some illegal matching, so some illegal possible choice. And for instance, you cannot have 2 triangle incidents to the same set of nodes. This would lead to a weighted simplicial complex, but not a simple simplicial complex. So you will have 2 triangles between the same set of nodes. So either you associate to them a weight, but if you don't, this is illegal. And you don't want, you know, 2 stubs of the same triangle incident to the same node, because this would not be a triangle. The 3 node incident to a triangle should be distinct. Okay, so you can take into account this illegal matching, and we have the code in GitHub. I think I have here the link to my GitHub page, in which we take into account this to not to consider illegal matching. And theoretically, we can consider the entropy. So practically, the logarithm of the typical number of graph that you get in if you fix the generalized degree as a hard constraint, like this algorithm, or if you fix it as a soft constraint, so with this marginal probability that I showed before. And from this theoretical result, you find that these ensembles are similar but not equivalent, meaning that this entropy is different from the 2, and it differs from by a extensive quantity. So you really need to consider the 2 models separately. And this analysis allows you also to calculate, you know, an asymptotic combinatorial number for the simplicial complex that you can get in this way. And these terms have each a combinatorial interpretation in terms of this matching that I described before.
Sorry, may I have a question?
Yes.
Would you be so kind to repeat definition of ensemble of simplicial complexes?
Yes, sure. So practically, well, I didn't give a real definition. So the definition is that you need to have a space, right? The space is the space of all simplicial complexes with n nodes. So you consider, as you, for instance, in the previous lesson, you have considered how many graphs there are with n nodes. It was 2 to the power n choose 2, right? So here you will have a space of all the possible simplicial complexes that you can construct with a node. So you can put, here we are considering pure simplicial complexes. So you work, instead of working with link, you work with triangle, and you consider pure simplicial complexes. So all simplicial complexes that are formed only by triangle and their face. Okay, so you calculate how many there are there. And then to each of these, you associate a probability. Okay, you say, in my ensemble, I associate a probability to each simplicial complex. And the ensemble is determined by your choice of this probability, right? You can say, I want to take all simplicial complexes of dimension d with equal probability, or you might want to refine your idea, because when you have a network or a simplicial complexes, these models are used to build null model. Okay, they are used to say, what do I expect from my data set if I only retain, for instance, the information that there are so many links, so many triangles, or what do I expect from an ensemble in which I fix the generalized degree? So how many triangular incidents to each node? Okay, and this framework allows you to construct the least bias ensemble which satisfy your constraint. Okay, and then, for instance, you generate this network, and then you can measure your observable. You don't know, you want to, you have a preferred motifs in your graph. You want to measure how many of these motifs are present in your data set and in this ensemble, and you compare the two in order to see if your data set deviates significantly from this null ensemble. Okay.
Thank you.
Okay. So practically, you have, in order to construct this probability, you have K, you have the entropy, and then you have to maximize the entropy given a given set of constraints. So you say, I want to have a model that is totally random, but that preserve the generalized degree of each node. And then this is the way to do it. And if you want more information about how you can really do this calculation, I point you to my lectures, 10-hour course on this. So, yes. So, and really, you in order to understand how much information do you put there in this constraint, right? You want to know how many graphs you can construct with this constraint, and this is given by this term, for instance, which in a network reduced to a famous Bender and Canfield formula that is known for these networks. Okay. This is a little bit of a technical observation. These simplicial complexes are correlated. So this can be measured by looking at generalized, the average degree of the neighbor of a node, or the clustering, how the clustering coefficient depends on the generalized degree and so on. And here, to conclude this part, of course, here we have constructed simplicial complex which are pure. What happens if I want to construct an hypergraph? Okay, so if I want to construct an hypergraph, I can use this model. I can use this model, you know, and draw first, for instance, a network, then a pure simplicial complex only formed by triangle, then maybe we only formed by tetrahedra, where I fix how many tetrahedra a node has. When you have a triangle, I fix how many triangle a node is incident to, and then I aggregate all these objects, and this is my hypergraph, right? Because I retain only the facet, I retain only the information about the link at the first layer, the triangle at the second layer, the tetrahedra eventually at the third layer, and then I aggregate all of them, and I have an hypergraph which contains both triangle, links, tetrahedra, and so on. And with this hypergraph, you can do, this is for people that know what a multiplex are, you can do some multiplex network analysis. So for instance, you can study the robustness of this network, and we have a recent preprint with my student on that. But this is just a diversion, is not the main subject of this lesson today. So let me now go. So we covered a bit of the combinatorial property of simplicial complex. What about the topological property? So topology is part of mathematics that studies shapes. So what happens? What is a invariant of a shape? If I do some, also I'm allowed to do some stretching and of the shape itself. And one important invariant, topological invariant, are the Betti numbers, which describe the cavity of the structure. And here we don't have the network yet, but it's just to give a good visual representation of this Betti number. So the circle is a structure which includes kind of it is a Betti number 1, which is a cavity of dimension 1, because it's the empty circle inside, the empty. So this, you have the circumference, and you have the empty at the in the inside. Then you have the sphere, in which includes a Betti number. A Betti number 2, because it's a two-dimensional cavity, and you can complicate the things, for instance, for the torus. And from these Betti numbers, and the first one only measure the connected component, you can construct the Euler characteristics, which is the alternating sum of this Betti number, which is an invariant of the structure. And of course, if you have a network, so for instance, this is a beautiful example of a fungal network in this very nice work in which there is a large data set of this fungus network. So here, of course, is a network, is not yet a simplicial complex, but you can think to do a clique complex of this. So you fill all the cliques here. And if you would fix the clique, you would find, of course, some cavity, some clear holes here, some loops. And this is also visually a very immediate representation of the importance of this hole for representing this structure. Of course, it's an important characteristic you want to capture. And what we did is to go also back to some very standard measure for network, like the clustering coefficient, and to show that also locally topology can be interesting. So for characterizing the topology around a given node, right? So you have a node, this blue point in the middle, with all its links. Okay, so this number of other nodes is equal to the degree of the original nodes, as they are the friend of the original node. And you look at their connection among them, you know, the connection among common friends. And you see that this network, you can perform a click complex, you can remove the node in the center, and this network can have different components. They can have different Betty numbers and so on. And interesting, the number of nodes in this network is the degree of the original node. And the density of links, you can do the math, it's very easy, correspond to the local clustering coefficient of the node, the original node. So practically, you can consider this ego-centered network, this neighborhood of a node that have the same, approximately the same number of nodes and the same density of links, but they can have very different topology. So when we look at different data, some have many disconnected components, some have just one connected component, and the Betty number changes. So really, also by looking locally at one very studied measure of clustering coefficient, you can distinguish between different realization of a clustering coefficient that can give rise to neighborhoods which are quite different topologically. So this is a work, a simple work that we have been doing in this direction. And another line of research, much more popular, is the one that studies the topology of a network with persistence homology. So this is a beautiful slide coming from the paper by Robert Gries explaining this persistent homology, and is a kind of visualization that starts from spatial nodes. So you are practically spatial point cloud. Okay, so now don't consider the network for a while. Let's focus on this point cloud. You want to understand how this point cloud can be characterized with topology. So what you do is, to every point you put a circle, and then you make this circle grow, and you form the simplicial complexes by connecting the center of this circle that overlap. You have a simplicial complex, and then you study the cavity, the Betty number of the simplicial complex as a function of the size of this radius that is increasing. And then you see, for instance, a connected component as a function of this radius, when they start, when they stop, when they die, how long they last. Or you can look at the cavity, so at the Betty number B1, at the cavity. This is the first, the second, the third, and you can see when they start and when they die. And the assumption is that an important feature of your data set is a cavity, for instance, that lasts as a long barcode, so lasts for a long set of value of this radius alpha. So this has been very popular field of topological data analysis. Is very, very rich. And in network, you can do practically the same operation when the network is weighted. Okay, instead of having this spatial radius that increase around the node, you have links, right, with different weight. And then practically you change the threshold. This is called a filtration. You change the threshold of these links from high to low, and you fill all the clicks of your network that are formed in this way, and you look at the persistent homology. And it has been observed in particular in this paper on brain functional networks. It has been shown that this procedure reveal differences that are quite important, and they are not revealed by other more traditional and combinatorial network science measure. Very interesting.
Can you back to previous slide?
Yeah.
Can you repeat, please, what does it mean epsilon and H0, H1, and H2 on the graph?
Yes, so practically you are following these cavities, right? So let me just, so epsilon is practically the radius of these balls. So you start with a small radius, and you see here, you see that there are different components, okay? As this radius increase, then there is only one connected component, right? So this means that for a certain epsilon, the connected component that you see is only this long one, long-lasting one, okay? So initially there are many, every node is a connected component. Then you increase the radius. Some node merge in different connected components. So some components die and merge with the other. And at a certain epsilon, you have only one connected component.
Okay,
And then the second, the green is the number of cavities. So you look at cavity of, kind of loops, not filled loops, and how long they last, because at the end you see there are no loops left. When the radius is very high, it's all dense, okay? So you follow this measure, okay?
okay, thank you. I catch the idea.
Okay, so you want to say that if, for instance, if a loop lasts for long, it means that the nodes are more or less placed on a circle, right? They are points, but they're more or less describing a circle. So another property of connected with topology is the notion of M-connected component. Of course, you have heard from the previous lesson that it's very important to study the connectivity of a network. So if you can go from a node to any other node of the network by following links. So you have this initial simplicial complex, which is connected. So if from any node, you can go to any node by following links. But then you have, so the zero connected component is one here. You have just one connected component, zero connected component. But then you can ask yourself, what are the one connected components? So components formed by links connected to links through triangles, or triangles connected to triangles through link. Okay, so you see the blue triangles are triangles that are not connected to any other triangles through a link. Okay, so they are separately one connected component. Then you have this component here in green on the top left, and then this component in green in the top right that is formed by triangle connected to triangle through links. So you can go from one to another passing through this link. And then you have the two connected components that are tetrahedra connected to tetrahedra through triangle. Okay, and you can go on and on. And this notion of connected component is equivalent to a very popular notion of community detection in network, which is called clique community. So of course, here you have a network, you need to do the clique complex, but then when you do the clique complex, you look at the M connected component, and you find these different, here called community, but are actually M connected component. Okay, so this is really topological description of this clique complex. Okay, so yes, so I want to also cover some geometrical aspects of simplicial complexes. Yes, so an important question that you have when you want to try to describe a simplicial complex with geometry is practically, you know, if you ideally want to use differential geometry, you know, one important question is whether your network whether you have any hope that your network can be describing something similar to a manifold, right? Because the whole theory there in continuous space is generally for manifold, while in network you are not guaranteed that your network is a manifold, so you need first to check this. And a way to check this is by looking at this incidence number, which is for a pure simplicial complex, the generalized degree -1 of the D-1 phase -1. So for instance, here the link 1, 3, right, as a generalized incidence number 2. Generalized degree 3, incidence number 2. So of course, this object here, intuitively, you understand, cannot really represent a manifold in the sense that it's not something similar to a surface because it has this kind of fin there, you know, and between node 1 and 3, right? It's a branching. And in particular, you can define when a discrete simplicial complex is a manifold, and one, it should be D-1 connected. It should have that, you know, be well behaved, but most importantly, this incident number can only be 0 and 1. So for instance, this object that we looked before is not a manifold, while if you remove one of these triangles, it becomes, because then the incidence number are only 0 or 1. And for this manifold, you can define, for instance, some notion of curvature, and one popular definition of curvature is the Regge curvature for this object, which is associated to the generalized degree of the node, because it's the number of, is 2 pi minus this dihedral angle. And if you assume that all the dihedral angles are the same, it's related to the generalized degree of that D-2 phase. So it's how, you know, 2 pi minus an angle multiplied by how many D-dimensional simplices are incidents to a D-2 phase. So this is a connection between geometry and, in some sense, the combinatorial property of your network, in this hypothesis that, you know, all the simplices are the same dimension. But this works for a manifold. So in general, you have simplicial complex which might not be manifold. So an important question is, what is a good definition of curvature? This is very much open. I mean, I am not covering here very interesting work on Forman curvature, Olivier-Ricci curvature. This is all very interesting, but for time constraint, I don't cover this here. But I want to mention the Gromov concept of delta hyperbolicity. So this is actually applies more than on a simplicial complex, really on a network. And the idea is that you want to characterize when a network is hyperbolic, right? And the idea is that you consider a good measure of hyperbolicity if you take 3 points in your network and the shortest distance between them. And then you want that this shortest path define what is called a thin triangle. So this shortest path, you know, they are a distance, they have a distance which is not more than delta. And delta defined is delta hyperbolicity. So let's see, for instance, in concrete. So a concrete example is a tree. In a tree, you have 3 nodes, this red 3 node, and you look at the shortest distance between these 3 nodes. So you have this green part here from the first 2, the pink part here, and the blue part there. And these 3 paths, they intersect at the node. So their delta is 0. So all trees are delta 0 hyperbolic. They are satisfying the delta hyperbolicity criteria very well. And here I show you another example of a simplicial complex, which is a kind of tree of triangles. You see, from each triangles you branch, and you look at 3 nodes, these 3 red nodes, the shortest distance between them, and this path, they are at most at distance 1. So this structure and its generalization is delta equal to 1 hyperbolic. And of course, in a network, in a real network, it might not be that this delta remains 0 or 1 for any node in the graph and for any size of the graph. But you have other ways to consider if your data set is hyperbolic. For instance, you can compare the maximum of this delta with the largest distance, the diameter of the network, and so on. But this is a notion of geometrical notion that has started to be developed for simplicial complex. And here I don't mention, but of course it will be crucial tomorrow, that you have, of course, the notion of Hausdorff dimensions, so how the diameter scales with the number of nodes, but you have also the notion of spectral dimensions, so what is the dimension that a random walk feels while walking on a network. And this notion of spectral dimension, we will cover it a lot in the next lesson tomorrow. So I don't know if you have any question. This is a good moment maybe to ask, or
any questions? Yes, there is.
Please, we jump to the previous slide. The right graph NGF, why we put the shortest way from the left node to the right node? Yes, not the upper one. Yes, this one. Why we put this not through the vertex which intersects with red path. It will be of the same length.
So you mean this one?
Yeah, yes. And in this way, we will have.
Yeah, you will have a delta equal to 0. Yes. Yeah. Yes, so you are right. Maybe this is not the best example. So for this, you could have a delta equal to 0, but in general, if you construct the simplicial complexes in this way, so that there are 3 of triangle, you might find that the largest delta is 1.
Thank you.
Yes. So of course, maybe this is not the best example. Yes, you're right. Thank you so much for noticing. In particular, you are always considering for any 3 nodes of your network, you are always considering the largest delta.
Okay. Also, we have some questions from chat box. Can I just read them? Thank you for your very much question. Another question. And the last question. Are there software to compute generalized degrees, centralities, etc. of simplicial complexes?
How to compute the generalized degrees?
Yep.
Well, if you have
Is there
this
any software to compute?
software,
Yeah.
yes, no, I don't have. But if you describe your simplicial complex with this tensor, right? A pure simplicial complex with this tensor, and then the generalized degree is given by this quantity where this is A alpha prime.
A alpha prime. Okay.
So you sum over all the simplices that include simplex alpha as a phase. So
There
it's
is
just
another question from Alec.
the sum in some sense of this tensor.
Okay, Alec, can you ask your question? Alec, can you ask a question?
Cannot unmute the microphone. Okay, we can probably continue, and then after the...
Очень вопрос задать, но он замьючен на уровне организации.
Yes, the question was actually...
Yes.
Okay, thank you. Actually, the question was, yes, the software, because you can represent your simplicial complex with this generalized adjacency matrices, but imagine if you don't just consider the triangles, which would be a 3-dimensional tensor, but the simplices of between 10 vertices and so on. So it would be very huge matrices, and I'm actually thinking about there should be efficient software implementations. There's such a software exists because you also need to compute probably generalized centralities, like between the centrality, closeness centrality, and so
on. Yes, so we have not conducted a lot of this analysis on the data. So we have worked on models. And for these models, we have kind of nice way to calculate the generalized degree. So for instance,
okay,
yes.
so you don't...
What we do to represent simplicial complex is general to use a cell, in MATLAB, we use a cell array where or it might not, it's good for spectral property, this cell array. So in cell array you represent all the nodes, all the links, all the triangles.
Yes, actually I'm modeling the data with the simplicial complexes, and yes, the simplest one is just to compute the spectral properties, but there are a lot of papers that consider generalize it, generalize some graph properties to simplicial complexes, and I think there is a lack of the software free in this area.
Yeah, maybe this is a very interesting question. Yes, open-ended. I mean, there is, of course, maybe different people have developed different framework. Of course, if you just are interested in the structure, you might just look at the facet of your data set. I mean, it's not important to consider all the subphases, and this might be more economical. But then if you want, for instance, to calculate the higher order Laplacian, which we'll discuss next tomorrow, then it's better to have all the facets to calculate this spectrum.
Thank you.
Yes, it depends on what you want. But yes, there is a lack in some sense both of data and of general numerical tools to treat this data. Still at the beginning. Yeah, so I had a lot of material. I'm only half of what I wanted to say. So, but maybe I can proceed a little bit for giving you a flavor.
There is still 20 minutes left.
Yes, I'll give you a flavor of what I wanted to say. So the second part here of this, ideally was the second part of the talk, was to describe some models, you know, how you can have models, not these maximum entropy models, which we described at the beginning, but non-equilibrium models of simplicial complex, which are a bit of a different philosophy. So you don't impose your constraint that you want to be represented on your network, but you set up a set of rules and you see what emerged from these rules. So it's a process that similar to what has been very popular in growing networks, starting from the BA model and so on. So here I want to discuss the first model, which is actually a model which we studied before this higher order kind of hype, but is really. Do you see my no? Probably okay. So it's really has been very inspiring for the rest of the work that we have done on modeling simplicial complex. Is a very traditionally a long-studied model of growing network with triadic closure, which is this assumption that a network evolved by closing triangles and is quite popular in social networks. But I mean, it's a quite of a very simple and basic model. So you start from a network, and at each time you add a new node. Here, to be simple, we have two links, for instance, and then the first link is attaching to a random node, and the second link is either close a triangle with probability P or is a link to a random node. So this closing a triangle is called triadic closure. And interesting, we studied the property of this model. For instance, this model is thought to be scale-free, but it's not exactly scale-free. It's broad, but it's not scale-free. And what we found is that interesting, this model generates community in a natural way. So that actually that there is this microscopic mechanism of closing triangles can induce a mesoscopic community structure in the network. And this is observe also in other model of simplicial complexes that we consider, so that, you know, the simplicial complexes and their evolution in time can lead to high modularity almost for free. And another question connected to this idea is a question of emergent geometry. Of course, we have discussed when there is a manifold, when there is no manifold, but you know, in nature, you have also this manifold, like here in this picture, it seems that this fiber really define a sort of manifold here in the brain, and a fungus, and this is an artificial model we generate. So what are the rules to generate this network that have an explicit geometrical interpretation? So is there a rule that doesn't take into account the embedding of the space and just is a combinatorial rule that can give rise to this emergent geometry? And so yes, so we want to look for combinatorial rules that only use stochasticity and combinatorics, and yet they generate geometry. So we consider, to start with, an example of two-dimensional simplicial complex. So we construct the simplicial complex with triangles, with the constraint that every link is incident at most to m triangles, when m is greater than 1. And then we have links we will call saturated or unsaturated, depending if they're incident exactly to M triangle or if they're incident to less than M triangle. And we consider two rules. Either, you know, we have a simplicial complex and then we stack a triangle to a link which is unsaturated, a random link that is unsaturated. Or, and this is a kind of one topological move, also called 1-2 Packner move in topology, or T1 move. And another move that we consider is this closing the pie, right? So you have a simplicial complex and then you put a triangle which is incidence to two link and two existing links, and it close this kind of pie. And by having a model in which process A is allowed for sure at each time and process B only allowed with probability P less than 1, we have a rich scenario of geometry, discrete geometry, and in particular if m equal to 2, so if every link is incident at most to 2 triangle, what we have is of course a manifold, because we know that this is the combinatorial condition to have a manifold. But here the manifold is generated only by combinatorial information. It's not generated by knowledge of an embedding space. And if m is infinity, so if we can keep adding a triangle to any link of the network, then we have a scale-free graph, so a network in which it is scale-free graph. And here you see the community with colors. So it generates a network which has distinct community structure already in it. And these networks are small world, finite clustering, and have high modularity. So, and also they have this additional feature that have a finite spectral dimension that we will cover a bit more tomorrow. So these are some of the analysis that we have done on them. So finally, let me use these 10 minutes to tell you a model which we are very, we have worked a lot on it. It's called network geometry with flavor, which generalized this initial model to a higher dimension. So instead of working only with triangles, you can work with tetrahedra and so on. So you have to start which you have a d-dimensional simplex, And then at each time you add a d-dimensional simplex to a face, and the probability depends on the incidence number of that face and a value S, which is called flavor, which can take values -1, 0, and 1. So if this flavor is -1, so you can generate only discrete manifold, because this probability becomes 0 as long as n alpha is equal to 1. So when n alpha is equal to 1, you cannot keep adding simplices to that face because the probability of adding it is 0. So what you are constrained is you only construct manifold. If the flavor is 0, this probability is uniform over all the d-1 face. And if it's 1, you attach a d-simplex proportionally to this generalized degree. So the more simplices are attached to that face, the more you want. And this is the kind of generalization of the preferential attachment mechanism to higher dimension. And if you look at 3 dimension, you attach this tetrahedra to a triangular face, and you look from above, you take a picture from above, you see that the initial triangle of this tetrahedra is then kind of triangulated into 3. Okay, so this is called 1-3 Pachner move also. So you can calculate the probability of attaching a d-dimensional simplex to a delta-dimensional face, and you can see the preferential attachment emerging also for flavor that are not 1. And so for flavor 0, we have seen in d-dimension that if I have a triangle that I attach to a link with uniform probability, I have actually an emergent preferential attachment, because I end up attaching a link to a node in proportion of how many links are connected to the node, so in proportion of its degree. And in 3 dimension, also if I have a manifold, I have an emergent preferential attachment. So here you have this manifold formed by 3 tetrahedra, and you look at node 1. Node 1 is incidence to 5 faces to which I can attach another tetrahedra. When I attach another tetrahedra to it, it becomes incident to 6 faces. So as I add d-dimensional simplices, the probability to add new d-dimensional simplices increases. So this is how geometry induces preferential attachment. Also, if I don't input that directly in the model, it's just induced by geometry. So in dimension 1, we have a manifold, which is a chain, or an exponential tree, or a preferential attachment BA model. This is the general picture we study in network science model. Preferential attachment is necessary to have a scale-free graph. But if you are in D equal to 2, also with uniform attachment, you get a scale-free graph, and the manifold is exponential. And if you are in D equal to 3, also the manifold itself becomes exponential, scale-free. So we can get the degree distribution. Again, there is this critical dimension at which you observe a scale-free degree distribution, and the analytical result go very well with the simulation result, asymptotic. They are asymptotic result. The code is available in our GitHub page, this code. And so you have this table, right, depending, it's not only the degree distribution, but it's also the generalized degree distribution. So how many d-dimensional simplices are attached to delta dimensional faces, which follow this very regular kind of table. So if you have preferential attachment, s equal to 1 is always power law. If it's s equal to 0 is exponential for d-1 phases, but power law for the other lower dimensional. and is S-1 is bimodal exponential and power law. So we want to end up with the notion of geometry of this graph. So this network, if you assume that all the links have equal length, you start with this initial triangle, this is d equal to 2, and you glue triangle to the links, this is the manifold in d equal to 2, and you see that the structure you can interpret as a structure of a hyperbolic manifold, which is actually a random Hypergraph. It's called Hypergraph, this object. And in 3D, you have, all the nodes in the surface of this sphere, and then you stack tetrahedra on it, and you get this simplicial complex there, which is a hyperbolic in 3 dimensions. So really, you can ask yourself, what is the natural random geometry, right? And you can say, well, natural random geometry is a random graph. So I consider all the possible links that are actually existing between n nodes, and I put them with probability p, and this is the answer of the mathematician. Then the physicist of the physicists of that study percolation would say, well, a random graph is a random cluster, right? A percolation cluster. I have a lattice in 2D, and I put links with probability p there or not there. This is my random geometry, and this is the traditional statistical mechanics physicists. And here we have yet another answer, is that practically this natural growth of this simplicial complex doesn't have an embedding space, but it generates like a growing cluster in this emergent hyperbolic lattice. So this is again this structure. So you can look at the surface, of the node here. You can stretch it, and you get this structure, which is this Apollonian graph. And this is clearly showing this geometrical nature of this graph, and in some sense, some holography of these networks. So, yeah. Okay, I think I stop here, and I thank you very much. I don't know if you want to use this minute again for a question.